Hey everyone, today we're gonna be looking at this I guess double integral. That's a bad name for it. It's not a integral. It's two integrals that I'm using to calculate the area between the curves, the two curves, the area that they bound. So here we have the integral going from 0 to 0 to 1.5 of the square root of x dx, and that here let me do that in green. That's going to be this curve here that I just traced out in green, and from it we're subtracting the integral going from 0 to 1.5 of 2 over 3x to 3 over 2 power dx, and that's going to be yellow. Yeah, I just leave it black. It's going to be the black curve there. As you can see, they share an area that they bound, and from it we can say that, well, one thing's for sure. The square root of x graph overall covers more area. Right? If we consider the area that the square root of x curve covers, it not only covers what the black curve covers, so this area, but also covers this area, and that's the actual area we're looking to find. So from it, the way we're going to do that is we're going to take the whole blue shaded region, and from it we're going to subtract just the area bounded by the black line, 2 over 3x to the 3 halves. And just to get a more clear representation, I have Desmos here to show blue line is 2 over 3x to the 3 halves, and then red is square root of x. I have x equals 1.5 to show where they intersect, and then we want this area bounded by both, or well, I guess bounded technically only by the square root of x, but we don't want this almost triangle looking area. Rather, we want this like slice of a ellipse or something. This area there. So in order to do that, we have these two integrals. So in order to solve this, we obviously have to integrate. So starting with the square root of x, if you notice, it is already integrated. That's the second integral. That's how you integrate square root of x. So instead, we're going to have right here 2 over 3 x to the 3 halves, just using like reverse power rule, going from 0 to 1.5, and from it we're going to subtract. Now we have to integrate this one, 2 over 3 x to the 3 halves. In order to integrate that, we use, once again, reverse power rule. So we add 1 and divide by, add 1 to the exponent and then divide by the exponent plus 1. Now that comes out to 4 over 15 x to the 5 halves, because 3 over 2 plus 2 over 2 is 5 over 2, and then 5 over 2 times, what is it, 2/3, you can simplify that. Or, well, you would have to take its reciprocal first because you're dividing, and then you can simplify. But you get what I mean. It'd be 2 times 2, because 5 over 2's reciprocal is 2/5, so 2 times 2 is 4, then 5 times 3 is 15. And we have this integrated integral, I guess. I don't really know what to call it. It's a bad 5. So now that we have it from 0 to 1.5, it really is just like a lot of number crunching, and I did this out almost all on hand. It was awful. So first thing we want to look at is, well, since the lower bound of the integral is just 0, we don't have to consider that. We only have to consider the 1.5 part. Now, if we plug in 1.5 for x, we have it raised to a fractional exponent, but not only that, the numerator is not 1. So what we do is we take the square root, because it's to the half power, and then we cube it. So we're going to do that. I don't want to use a calculator. Instead, we're going to take the estimated square root of 1.5. So we don't know what the square root of 1.5 is, but we know that the square root of 1 is 1. And the derivative of square root, a square root function, is 1 over 2 square root of x. So what we're going to do is we're going to multiply that by the difference between 1.5 and 1, which is 0.5. Simultaneously, we're going to plug in 1 for this. So here, let me do it down here. That gets us, well, square root of 1, like I said, is 1. Times 2 is 2. 1 over 2 times 0.5 is 0.5 over 2. 0.5 over 2 is... What is 0.5 over 2? Where did my... Oh, it's on a separate piece of paper. .25. Yeah, that makes a lot of sense. I don't know why it took so long to get that. So, 0.5 over 2 is in fact 0.25. Okay. And we're going to add it to 1, because that's the original square root we have, and that's 1.25. Let me get some more space. Let me 1.25. Yeah, well, whatever. So that means that the square root, or the estimated square root of 1.5, is approximately equal to 1.25. So now that we know that, I'm going to erase this. Now that we know the approximated square root of 1.25, we know that this is going to be a pretty rough approximation of the integral, but you know, it's whatever. We now have to raise it to the third power, so 1.25 cubed, and I definitely, not the square brackets, the round ones. Definitely recommend doing this just on a calculator, but I did this out on hand and checked with the calculator. It was absolutely awful. But 1.25 cubed is 1.95325. Now we do that's not all. We now have it cubed. We now have to multiply that by 2, then divide by 3, because we have 2/3 as our coefficient. So when we multiply that by 2, we get out. I'm not going to have enough space. Where is my calculation for that? I don't want to do this out on hand. It's okay. Here it is. 3.90625. Now that we have it multiplied by 2, we now divide by 3. And this is going to get us, I'll write it down here. This is going to get us 1.30283 repeating. 83 repeating. So, all in all, our first integral, so, I probably should have labeled those. Alright, so we'll do, where's my cursor? It's gone. Here. We'll do I sub 1 is approximately equal to 1.302083 repeating. Now that we have that, I'm going to erase this and calculate our second integral. I sub 2, I guess. And then we'll subtract. So now we have to do 1.25 to the 5th, which I also did out on hand. Just use a calculator, it's so much faster. 1.25 to the 5th is, ooh, this one's a long one. 3.05717581225. And now we multiply this by 4. So times 4. that is equal to, where is my, where did I do that? I should have organized this, like, way better. Oh, here it is. Okay. It is equal to 12.2070 3125. Now, of course, we have to take that and now divide by 15. So we take this, divide it by 15, and this is equal to, what is this equal to? That is a great question. I believe it is equal to I need more space. 0.13802083 repeating. I believe that is what it's equal to. Let me break out the calculator for once and actually find out. 12.027. Oops. Nope, we're good. Yep. Oh, did I forget a 0? Oh no. It's just, okay, shift that over by a little bit. Okay, yeah. That is correct. So this is I sub 2, our second integral, is equal to that. So now, let me erase all this number crunching garbage and properly show what this integral is equal to. So we have our integral, I'm just going to use I sub 1 minus I sub 2. I don't want to write the whole thing out. Is equal to, or well, I guess approximately equal to 1.302083, repeating, minus 0.813802083. Forgot the repeating. Oops, I think I erased that. Repeating. So I also did that out on hand, except without the repeating, because that's annoying. And it is approximately equal to 0.4882809117. So this is what our bounded area is approximately equal to. Not a super satisfying result, considering it's not a lot of calculus, a lot of number crunching, and just using a calculator. Which is why, if Wolfram Alpha open, we have the actual answer. It's so our first integral, I sub 1, is 1.22474. So let me break out the calculator again. 1.22474 minus our second integral, I sub 2, is approximately 0.73847, and this culminates to 0.489893, which, if you compare to our approximation of not only not having an infinite number of 3's, but also estimating our square root, it's not a bad result. We're pretty close, but super unstructured, super unsatisfying, and I'm sorry about that. Not a super cool video to watch. A lot of using the calculator, not a lot of actually thinking, but that's our integral. That gets us the area in between these two curves, which I thought was at least a cool concept, even if the method for getting the answer was not all that fun. Anyway, that's it. Thank you for watching.